So we've looked at sequential data and sequence-to-sequence layers in general. Now let's look at a specific sequence-to-sequence layer, namely the recurrent neural network. And a recurrent neural network is basically a name for any neural network that has a cycle in it. So far we've only looked at feed-forward neural networks, where all the connections flow in one direction. But a recurrent neural network is one where we can have a cycle between two nodes. So connections that flow from one node to another and then back to the original node. There are a lot of variations. Here is one of the simplest ones called an Elman network. And for an Elman network, basically we start with a normal two-layer feed-forward network with sigmoid activations as we've seen it already. And then the cycle that we add is that the hidden layer is concatenated to the input layer and used as an additional input. Before we move on, here's a little visual shorthand that will help us write down these networks and draw these networks in simpler terms. So I'll represent a layer, which is a vector of values, by a bar, either a vertical or a horizontal bar, in this case horizontal. When one layer feeds into another layer, we'll represent that by a line, possibly with an arrow to indicate the direction. If there's a capital letter next to the line, that indicates that we're multiplying the input vector by a weight matrix, and we assume that for every weight matrix there is also a bias vector, which we don't indicate. And in this way we can very simply draw neural networks. And this is the basic feed-forward neural network that we've been drawing a lot already, represented in this new kind of visual shorthand. And on the right are the equations that tell you more precisely what is happening here. So now, in this visual shorthand, we can represent our recurrent connection in this way. So at the top we see a bifurcation in the arrow, which indicate that the value splits off before we're multiplying the weight matrix phi. And at the bottom it joins another line, by which we mean that the two vectors traveling, as it were, along these lines are concatenated before they are multiplied by the weight matrix phi. And that concatenation, as you can see in the formulas on the right-hand side, we represent by drawing these vertical bars. So this represents the concatenation of the weight matrix xt with the hidden layer h at time step t minus 1. And because this is a recurrent neural network, that means we should view it as operating at that means that we should view it as operating over time. At each time step, we do one forward pass, and then at the next time step, we do another forward pass. So let's have a look at what that looks like. Here is the network at the first time step. And we have, as you can see at the bottom, we have an input sequence, x1, x2, x3, and so on. And we set the first hidden input, and we set the first hidden input, h0, to the 0 vector for now. So for the first time step, we have all we need. We concatenate h0, which is a vector of zeros, to x1. We multiply this concatenated vector by the weight matrix W, which gives us the first hidden layer, H1. That moves up, gets multiplied by V to produce the first output vector, Y1. Meanwhile, this first hidden layer travels over the recurrent connection to become part of the next input. So at the next step, we take the second part of our input sequence, X2. We concatenate it with H1, we multiply the result by the weight matrix W, which becomes the hidden layer H2. That hidden layer travels over the recurrent connection to the next time step, and H2 also is multiplied by the weight matrix V to become the output Y2. So note that we are step by step building up our output sequence. And we continue in this fashion until our input sequence has been exhausted. So now the question is, how do we train these networks? Because it's very easy to compute the forward pass in this way, but at time t, the network of time t minus 1 has already disappeared. The trick, of course, is not to let it disappear, to keep it in memory and to perform what is known as backpropagation through time, we remember the history of our entire computation as a computation graph, containing lots of copies of our network as we evaluate it through history, and then we backpropagate through this history. And the easiest way to think of this is as an unrolling of our neural network, which looks like this. So here we have rotated the vectors by 90 degrees to make them vertical bars. And basically we see here the forward evaluation of the neural network at every time step. So note that at time step 1, the first element in our input sequence is concatenated to the 0 vector h0, fed into the first layer, and produces the output y1. And the recurrent connections are now connections from left to right. And if we draw our network like this, it's nothing more than a basic feed-forward network, which we can implement and call a backpropagation on. So for instance, if we follow the loss between the last element in our sequence drawn here, between the element y6 and the target element t6, then we see that the backpropagation signal simply travels all the way back through history down the network and computes gradients that allow us to update the weights W and V. Now, of course, these are shared, these matrices W and V, over all of these time steps, but we know how to deal with shared weights. We simply sum up all the individual gradients that we get for this backpropagation step. If we have a particularly long sequence, we can make things a little bit easier for ourselves by applying truncated backpropagation through time, where we compute the forward pass over the whole sequence, but we do the backward pass only over part of the sequence. And the nice thing there is that we don't need to store the computation graph for the entirety of the sequence. We only need to store a computation graph for the part of the sequence that we're actually going to backpropagate over. And this first part up to h3, we're not actually using any memory to store all our computations, even though the final value of the sequence, y6, still depends on the entire forward computation on the whole sequence. So that's recurrent neural networks. These are some important properties. First of all, note that they are sequence-to-sequence layers by the definition that we had in the previous videos. We have a single set of shared weights which we can use to expand the RNN to any length of sequence that we encounter. RNNs are strictly causal sequence-to-sequence layers. We have recurrent connections and they can only look backwards. So the output at a particular time can only look at the inputs of the previous time steps and the current time step as inputs. So all RNNs are always causal. And note that the nice thing about RNNs is that they have potentially unbounded memory. If we unroll over the whole sequence, there is a computational connection between the first element of the input sequence and the last element of the output sequence, no matter how long the sequence is. And this is where they differ from, for instance, CNNs, because we know that CNNs, as we can see on the right, have a finite receptive field. So any of these outputs in the CNN can only depend, if we have one convolutional layer with a size 3 kernel, then any output of this CNN can only depend on 3 of the inputs. And it cannot look infinitely far along the input sequence, in contrast to the RNN, which can always look infinitely far back in the input sequence. The drawback, the price we pay for this potentially long memory, is that RNNs are quite slow to evaluate because they need to be processed sequentially. What that means is that in order to evaluate the hidden layer H4, we first need to evaluate the hidden layer H3. And in order to evaluate that, we first need to evaluate the hidden layer H2, and so on. We cannot evaluate these 4 hidden layers in parallel. Contrast that with the CNN, where if we look at the 4 outputs, each output can be given to a thread, which in parallel computes that particular output based on the weights of the convolution and the inputs. And they don't need to refer to each other in order to know their own value. And this makes RNNs a little bit slower than most other neural network layers. In the previous video, we saw a few tricks for how to wire up sequence-to-sequence layers for sequence-to-label tasks and label-to-sequence tasks. RNNs allow us a few extra options here. For instance, if we have a sequence-to-label task, what we can do is take the last hidden output of the layer and make that our label output. Similarly, if we have a label to sequence task, we can take this hidden state that we initially set to 0 and actually set it to be our label input. And this very nicely keeps our input sequence free for another input. So if you want to do label to sequence and sequence to sequence, feed the network both with an input sequence and a label input, then this is a very natural way to do that in recurrent neural networks. Note, however, that the other approaches that we saw in the previous video, like a repeat sequence and a global pooling layer, also work on RNNs, and in some sense are probably better options, because what you see here is that between the label input and the last output, there is a very long sequence of many computation steps. So actually for the last output to depend on the label input requires a lot more fine-tuning of weights than for the first output to depend on the label input. And if we feed the label input as a repeat sequence, that becomes more equally and uniformly distributed. Nevertheless, this is a neat solution that you do often encounter in implementations and models in the literature. Now, as I said before, RNNs have a potentially unbounded memory. That's a very nice promise, but unfortunately in practice it isn't really the case. They have a potentially infinite memory, but practically they have a relatively short memory. When we do train them, we see how far back in the sequence they do actually remember things. They don't remember more than a few steps back in the training data. And the reason for that, you can see in this picture. We can see that as the gradient travels back from the last element of our output sequence, it has to pass through a sigmoid layer for every time step. So what we see here is the vanishing gradient problem that we also saw in deep feed-forward networks. Every time this gradient passes one of these sigmoid activations, it is multiplied by a factor of at most 0.25. And if these weight matrices are poorly initialized, then ultimately the signal will be pushed into one of these regimes of the sigmoid where the gradient gets even lower and ultimately vanishes. Now, of course, we could solve this by replacing the sigmoids by ReLUs and by making sure that the weight matrices are properly initialized, and perhaps even by adding the occasional normalization step in between. But in the late 90s, when these recurrent neural networks were very popular, those options weren't available yet. And instead, people came up with a very different solution, which is known as the LSTM. And the LSTM is what we'll be discussing in the next video.